Okay, so it's 12 o'clock. It's around time for us to get started. I think I got everybody's test back. I've only got 2 or 3 left in my folder, so if you didn't get yours, just let me know. I do have them and can give them back. Before we get started for today, are there any questions about anything? Okay, last day we did capacitors in series. We talked about capacitors as circuit devices. We're going to keep going with capacitors today and do some capacitors in parallel, and we should be able to get to talking about energies in capacitor systems as well. So for our capacitors in parallel, parallel is just a different way of connecting two objects. So in series, they were all in a row. In parallel, they're connected top to top and bottom to bottom. So this is something everybody would have seen in the lab at this point. So when we talk about parallel connections, you go from your battery and you connect one set of wires right into your capacitor. So you might picture this as sort of orange covered wires going straight in that capacitor. When you look at this, the capacitor goes straight to the battery. There's no potential difference loss along the way because we've got our perfect wires. That means that the potential difference across the capacitor has to be equal to that of the battery. For our next connection, we take another set of wires and we go on top of that battery and we go to the next capacitor like this. If we look at that connection, we see that the capacitor goes straight to the terminals of the battery. It has to have the same potential as the battery. And then we put in one more capacitor, so we've got a third set of wires, and we go straight from the battery to the capacitor C3. So C3 is connected directly to the terminals of the battery. C3 has to have the same potential as the battery. So that's the difference between parallel and series connections. Things in series, capacitors in series all have the same charge. Capacitors in parallel all have the same potential. So that's going to be an important one to remember as we go through this section. So let's make a note about that. So all capacitors are connected directly to the battery. Therefore, they all have the same potential. So that's one thing we know about parallel connections. Anything connected in parallel has the same potential. So that takes care of that bit. Now let's think about the charge, because we know when we hook up a capacitor to a battery, charge starts to flow around. And charge will flow until the capacitors get all charged up. So if we think about what happens in the charge flow, we get an amount of charge is going to leave this battery. So charge Q comes out of the battery. And look at what happens when it gets to this point. The charge has a choice to make. It can come down to C1 or it can keep going. So some charge can come down and some charge can keep going. Okay, because we've hit a split, it's got 2 wires to travel on, it can go either of these 2 paths. The amount that comes down here, we call this Q1. When this bit of charge, the bit that kept going, hits this point, it has 2 choices. Some of it can come down, we could call that much Q2. Some of it could keep going and would hit capacitor 3, and we would call that Q3. So the total amount of charge has to get divvied up over the 3 capacitors. So the charge has to split. So that's our potential relationship. And the charge, the net amount of charge leaving the battery, splits over the capacitors. And overall, we can't have any loss of charge because there's nowhere for it to go, right? It's not going to fall on the floor somewhere. It has to go to the capacitors. So because the charge splits, we can write that our total amount of charge that's output by the battery is equal to the net amount of charge that ends up stored on those capacitor plates. There's our net charge. If we wanted to think about what these Q1, 2s, and 3s are, let's remember that each of these batteries has the same potential because they're batteries. Each of these capacitors has the same potential because they're connected in parallel to the battery. So if we remember our relationship between charge, capacitance, and potential, we know that Q is equal to C times delta V. So Q1 is C1 times delta V. Q2 is C2 times delta V. Q3 is C3 times delta V. Okay, so far so good? So the charge splits, it depends on the capacitance and the potential. So now let's take the same idea that we talked about last day. Last day we said we could take out our 3 capacitors that were in series. We could pop those 3s out. We could put in a brand new capacitor. And if we pick the right capacitance, it will give us the same amount of charge for the same potential. We can do the same thing here. And that's called an equivalent circuit. So to go from here to here, we make an equivalent circuit. And what that means is we take out these 3 capacitors that are connected in parallel. We put in a single capacitor, and for the potential of the battery, delta V or epsilon, we get exactly the same amount of charge delivered. Okay? So same delta V, same Q, and we figure out what our equivalent capacitance is. So in our equivalent circuit, CKT for circuit, our equivalent circuit has capacitance that we call CEQ, it has the same amount of charge and the same potential. These are the same as the original circuit. So that means our equivalent capacitance is related to delta V and Q. C equivalent is equal to Q divided by delta V. So now what we can do is look at this equation. If C equivalent is Q over delta V, then the net charge Q is C equivalent times delta V. We can take that and plug it in over here in this equation. So C equivalent times delta V is C1 delta V plus C2 delta V plus C3 delta V. We notice we have delta V in all terms on the right and the left-hand sides. You can divide through by delta V and see that they cancel. And that leaves us with the result. C equivalent for capacitors connected in parallel is C1 plus C2 plus C3. So that's how we find the equivalent capacitance for capacitors connected in parallel. People remembering their high school physics might remember this is the equation for resistors in series. We're going to get the resistors in our next chapter or two. Please don't get them confused. Make sure you know your rule for your circuit device. So this is the equivalent capacitance for capacitors in parallel. Okay, all good? Okay, let's get into some examples. So let's take a simple network. Let's take a battery. I tried to draw it a little bit funny just so you get used to seeing some funny pictures. So we get used to recognizing how we know if things are in parallel. So I've got 3 capacitors. You can call them C1, C2, and C3. We want to find the charge on and the potential across each capacitor. So if we look at capacitor C1, we can see that it goes straight from a set of wires to the battery. Likewise for C2, it can go straight from the wires to a battery. And C3 can go straight from the wires to a battery. These are all connected in parallel. So this is a parallel connection. Right off the bat, when we see things connected in parallel, we know that they have the same potential. So delta V of capacitor 1 is equal to delta V of capacitor 2 equals delta V of capacitor 3 equals delta V of battery, which was given as 9 volts. So right off the bat, if things are in parallel, that's an easy question to answer. They all got the same potential. Okay, the next thing we're asked to find is the net charge on each capacitor. So we know each of the capacitances, we know each of the potentials. It's going to be easy to find each of the charges. So for our charges, Q1 is equal to C1 times delta V. So C1 is 12 picofarads, or 12 times 10 to the minus 12 farads, times my potential 9 volts, gives me 108 times 10 to the minus 12 coulombs. And if you preferred to write that as 108 picocoulombs, that would be just fine. Likewise for charge 2, C2 times delta V, 22.1 times 10 to the minus 12 farads times 9 volts, gives us 199 times 10 to the minus 12 coulombs. And then we can do Q3 as well, C3 times delta V, 57.9 times 10 to the minus 12 farads times 9 volts equals 521 times 10 to the minus 12 coulombs. So we see that the ones with the biggest capacitances can hold the most charge. If you wanted to, with this problem, you could find the equivalent capacitance, and then you could use this delta V. If you took your equivalent capacitance and used this delta V, you could find the total charge stored, and that should give you the sum of these three things. So that would be a step you could do if you wanted to. Any questions? That step's pretty straightforward. Okay, let's do slightly more complicated circuits.
Say you did go about it that way you were just describing, like going through C, E, Q. Is there like, okay, so if you added up all those capacitance and then divided each of them by the total and you got a ratio, could you use that ratio to get like the different values of Q? Like, you know what I mean? Like, is there a way to go
Yes,
that way?
it feels a bit needlessly complicated,
Yeah.
but you certainly could.
Okay.
Because you can see that the bigger capacitors hold more charge. That's certainly true. So if you found the fraction of the capacitance as a fraction of the total, you could find that same relative fraction of charge.
Right.
Yeah, physics-wise, that is definitely not incorrect. Yeah.
Cool, just curious.
Yeah, sure, no problem. That might come in more useful where the capacitors are sort of like doubles of each other.
Yeah.
That could be a quicker way to do it with kind of random numbers. Let me just bog you down. Okie dokie. All right, so when we have real circuits, this sort of thing, there's not a whole lot of having 100 capacitors connected in series or 100 capacitors in parallel. Really, you've got a handful in series, a handful in parallel, and then they're all woven in and out with each other. So most typically in real circuits, we have combination circuits. Some of them are series, some of them are in parallel. We can still use our tools to analyze those circuits. We just have to take it step by step. So I've started with a pretty simple circuit. And what we're asking is let's find the equivalent capacitance of this system of capacitors. So to start these, you have to look and you have to ask, do I have any obvious parallel connections or do I have any obvious series connections? You start with the obvious ones, you draw a picture, keep going until you get to the end. So let's look at this. Let me throw it out there. Does anybody see any obvious series or parallel connection? Any straight in a rows or tops to tops and bottoms to bottoms?
Yes.
Yes. With C1 and C2? Yeah. These guys are definitely in parallel because C1 comes down here to these 2 points. C2 comes up here to these 2 points. They connect to exactly the same points. So they both connect to right here. That means they have to have the same potential, which means they're connected in parallel. So C1 and C2 is our starting point because we can see that they're connected in parallel. So we look at our diagram and say that these are a parallel combination. C equivalent for parallel combinations is when we just straight up add together the capacitances. So 10 picofarads plus 5 picofarads gives us 15 picofarads. I could write times 10 to the minus 12s for my pico there, but I'm not going to because I don't want to. So I'm just going to work in picofarads. So once we have this bit done, we have to draw a new circuit that has our equivalent capacitance in it, and then we have to look at that new circuit. So we've got our point A. It comes over here to an equivalent combination of these two. That's our C equivalent parallel. What we might remember, we're not going to do any work on it in this problem, is because these two are connected in parallel, C1, C2, and C equivalent parallel, they all have the same potential because that's a parallel combination. So we're going to have to be thinking those things as we go through our problems. So there's my point A, there's my point B, there's my parallel equivalent, and there's my C3. This new diagram, sometimes this gets a few people. So what would the connection here be?
Series.
That one is a series. And it's sort of set up to look a little bit like parallel, because you see one is sort of on top of the other. What you gotta do it with your finger if you want to, is trace, are they in a row? So the charge that comes out of A hits this plate, then leaves this plate, carries along the wire, hits the next plate. If that charge flows in a line like this, that means it's a series combination. So that's how you can tell series, because it goes all in a row. So these are a series combination. For our equivalent series combination, 1 over C equivalent is 1 over this one, C equivalent parallel, plus 1 over this one, C3. 1 over 15 plus 1 over 15. At this point, you're either going to go fractions or calculator. I'm more of a fractions than a calculator, so 2 over 15. And to find our C equivalent, we have to take the inverse of both sides, so 15 over 2, or 7.5 picofarads. Then to finish our problem, we draw that very last step with the 2 series taken out and our equivalent put in. Point A, point B, C equivalent. Our series combinations, they have the same charge. And our parallel combinations, same potential. Okay, questions? So that was a simple one to get us used to the process. Let's kind of take it up a little bit. So for our next one, this time we've got 5 capacitors. We know the potential difference across A and B, so the total potential difference as we go from here to here is 25 volts. We've got 5 capacitors along the way, so they're going to have their own individual charges and potentials. And the first thing we're asked to find, what is the equivalent capacitance of this system between points A and B? So we want to take this and we want to break it down to an equivalent. So when we're going to start when we're gonna start our analysis, we look at obvious connections. Anything jump out at anybody as a place to start? For me, I'd start with these two. Okay, and the reason I like starting with these two is, to me, they're very obviously in series, right, because they're in a row. And because when I look at this, I see that this branch is in parallel with this branch. I know I'm gonna wanna simplify this branch. So to me, this is my starting point, is recognizing that those two are in series. So I'm gonna start there. I remember that when they're in series, they have exactly the same charge, so I'm going to be wanting to be thinking about that. I know I have to do the reciprocal, so 1 over C equivalent is 1 over the first capacitance, 1 over 6.2 microfarads, plus 1 over this capacitance, 1 over 11.8 microfarads. If you were a fractions kind of person, you could totally deal with that in fractions. I think for me, I'm going to a calculator on this one. 0.246 microfarads to the -1. Take the inverse of both sides to get that my C equivalent is 4.06 microfarads. Okay on that step? The next step in our process is to redraw our diagram. We're taking out these two and we're putting in this equivalent. So I'm going to redraw it. Point A, I've got these two capacitors. I've got my branch that comes up at point B, and then I've got this branch. This one is my 4.06. This one is my 3.50. For my next obvious connection, I want to deal with these in parallel. So I can see that they're in parallel because the top ones and the bottom ones, they connect to exactly the same point, so they have to have the same potential. It means they're in parallel. So these are a parallel connection. When things are in parallel, they have the same potential. To get my equivalent, I just have to straight up add the numbers together. 4.06 plus 3.50. So that gives me 7.56 microfarads. Okay. Next, I have to redraw my circuit. I have to take out those parallel, and I have to put in the equivalent. So I've got my point A here. My first capacitor is the 8.6. My next capacitor is the 4.8. And then I've got this parallel combination, which was 7.56 microfarads, and then that connects to point B. Okay, I've got 3 capacitors. They're all connected in a line. That tells me it's a series combination. So I can finish by finding the equivalent of that series combination. One over C equivalent is 1 over 8.6 plus 1 over 4.8 plus 1 over 7.56. So 1 over C equivalent is equal to 0.457 microfarads to the -1. Take the reciprocal of both sides, and our C equivalent is equal to 2.19 microfarads. And then to finish, we'll redraw our circuit for the last time. Okay, any questions to here? So there's our part A done. It was a fair bit of work. I'm going to say that when you do these problems, it is important to show all of these steps. I will be looking for these steps on a test. And if you go from your first picture on a test to this last one and say, I did everything in my calculator, I'm going to say, great for you, you get 1 out of 10. Okay? So I need to see that you know the steps and what the connections are and how you put it all together. So I'm definitely looking for all these steps when you do it on a test. So that takes us through part A. Part B, how much charge is stored in this system? Part B becomes pretty easy to answer because we know the potential across AB. We know the equivalent capacitance. If we know potential and capacitance, we can find charge. Okay, so this is an equivalent that gives us the total charge stored in the system. So part B, we know that Q, our net charge, is C equivalent times delta V. Delta V means the potential difference across points A and B. So I've got 2.19 times 10 to the minus 6 farads times my potential difference, that was 25 volts, gives me a net amount of charge 5.47 times 10 to the minus 5 coulombs. And if you gave it as 54.7 microcoulombs, that would be fine too. Okay, still good? So now, how much charge does the 3.5 microfarad capacitor store? So now what we're trying to do is take, well, right here I learned what the total charge is. Now I'm trying to figure out how much of that total charge is actually on this capacitor. Here's where you have to take everything you just did and work backwards. So we're going to work all of our steps backwards, figuring out charges and potentials as we move backwards, remembering that series is same charge, parallel is same potential. Okay, so I could draw on these diagrams, but they actually look kind of neat and I don't want to mess them up. So I think I'm going to start a new system of diagrams, and I'll show you where each step comes from as we draw it. So for part C, let's start with the fact that here's point A. Here's my equivalent capacitance of 2.19 microfarads. I know the potential difference here and I know the charge here. 5.47 times 10 to the minus 5 coulombs and 25 volts. Okay, so that's just a recap of everything I know so far. I want to back up one step. So my last step before I got to here was this step right here. So I had point A, 8.6 microfarads, 4.8 microfarads, and 7.56 microfarads between my point A and point B. So now we have to remember, how is this picture connected to this picture? Well, this one is the series combination of these three. So that was a series combination. What we remember about series is that they all have the same charge. So each of these three capacitors all have the same amount of charge that we found right here in part B. So underneath my 7.56, I'm going to write down what that charge was. 5.47 times 10 to the minus 5 coulombs. The reason I'm targeting this 7.56 is because of where I came in my steps. This 7.56 was the parallel combination of these two. That's where the 3.5 was hidden. That's why I'm looking at this one. If I know the charge and the capacitance, I can find the potential. So I can find the potential across this capacitor. So delta V is Q over C. Q over C. I think my handwriting's starting to get small. I'll zoom in a bit. Q over C. So this charge divided by this capacitance gives me 7.24 volts. If we just stop briefly and do a does this make sense check, this potential is less than the total of 25 volts, so yeah, that pretty much makes sense. If we got here, 57 volts, that would be too much, and we definitely goofed somewhere. So we're looking good to right here. We're going to back up another step. As we back up to our next step, we're going from this picture backwards to this picture. So let's redraw this diagram. So our previous step had point A here, our two connected capacitors here, point B here. This one was our 4.06, and down here was our 3.50. So let's ask about the combination. This 7.56 was a parallel combination of the 4.06 and the 3.5. So as we backed up, this was a parallel combination. What we know about parallel combinations is same potential. So on this 3.5, we can go ahead and write 7.24 volts. Okay, and it has to be 7.24 because all things in parallel have the same potential. Our question asked how much charge was there. So the amount of charge Q is going to be C times delta V. So 3.5 microfarads times 7.24 volts gives us 2.53 times 10 to the minus 5 coulombs. Okay, so that's our answer to part C. And then if we glance ahead to what question D asked, oh, I can't get it all in the picture. Zoom out just a tiny bit. Part D asked what was the potential difference across the 3.5. We actually found that as we went through part D. Sometimes, especially depending on if your brain works a little bit differently than mine, you may end up finding these out of order, and it's always fine to do them out of order because there often tends to be slightly different approaches to a given problem. Okay, any questions? All right, excellent.
So, yeah, actually, can you just run through that process of getting charge for the 3.5 microfarads?
Right here?
Yeah.
I just did C times delta V. I know the capacitance, because it was given in the diagram,
Right.
and I knew the potential because this one right here was the parallel combination of these two. That means this one, and this one all have the same potential. So what I found here for this potential had to be this potential.
So you use the 7.56 microfarads to get that potential.
Exactly.
Okay.
Yeah.
And then they're in parallel, so then they have the same.
Yeah.
Okay.
Okay, let's do a couple more examples. So for this page, there's two questions on the same page. So I've got two capacitors, 4 microfarad and 8 microfarad. First question says, how can I hook them up? And how can I hook them up means series or parallel. To get them 4 microfarad a greater potential difference. And then how can I hook them up to give the 4 microfarad a greater charge? I'm going to give you a hint, and I think this is fair game in class, although I might not do it on a test. One of these is a trick question. Okay, so let's go through it and see if we can figure out the trick question. I do tend to be more straightforward on tests, like I know that's a higher anxiety situation, but I think we can be a little trickier in class because the stress is a bit lower. So we've got two capacitors. We want to hook them up, and we know that we care about the potential difference. You might have an idea right off the top of your head about how you could hook them up, but you would still have to justify your answer. So to figure this one out, why don't we look at the series combination, why don't we look at the parallel combination, and why don't we draw our conclusions after we've looked at both? So that's a good solid strategy to look at this problem. So parallel, and as soon as you write down this word, you might write in brackets, same potential. And as soon as you write down same potential, you might discard this as the correct answer. Okay? Because we're asking how do we hook it up to give one a bigger potential? Well, clearly it can't be this way because that's the same potential. But let's go ahead with our diagram all the same. So for a parallel connection, we'll have one capacitor on top. I'm going to call that one the 8 microfarad. One capacitor in the middle, that's going to be our 4 microfarad. And then they're both connected to a battery that has some potential delta V. So they both have the potential delta V. This one is not our answer. Let's go to our series combination. For series, we remember same charge. As soon as we write that down, we think, okay, series could be our answer. If it has the same charge, different capacitances, it's going to have different potentials. So we've got some hope here for this one. Let's draw them in series. So here's my first capacitor, 4 microfarads. Here's my second capacitor, 8 microfarads. And here's my battery with potential delta V. So let's think about I could go ahead and do all the math, give myself a potential difference and calculate the charges. Let's try to be a little bit more slick about it. My potential across my 4 microfarad capacitor, I'm going to call that delta V1. That's the charge on it, divided by my capacitance C1. Okay, so that's how I would find the potential across that one. Likewise, on my second one, so call this one C1 and this one C2. On my second one, delta V2 equals Q over C2. Those charges have to be the same. I called my C1 4 microfarads and my C2 8 microfarads. So right off the bat, I see that C1 is less than C2 because of how I labeled them. If this number is smaller, then my delta V1 has to be bigger. The delta V1 is greater than delta V2. So the answer to my question, how could I connect them to get a bigger potential on this guy? I would have to do a series connection. So to get a greater potential difference, I would connect them in series. Okay, any questions there? Okay, next bit. So I guess now we've identified which one is the trick question since it wasn't the first one. How can we connect them so that the 4 microfarad has a greater charge? So right off the bat, if we continue thinking about our series combination, series 1 has the same charge, so that's not the answer. For our parallel combination, so C1 for my 4 microfarads, C2 for my 8 microfarads. For my parallel combination, C1, my 4 microfarad capacitor, my charge Q1 is equal to C1 times delta V. Remember, they have the same potential because they're connected in parallel. For my second capacitor, C2, that's my 8 microfarads, Q2 is equal to C2 times delta V. Let's apply sort of the same thought process here. What does knowing the relationship between the capacitances tell us about the charges? C1 is less than C2 because 4 is less than 8. That means Q1 is less than Q2. So the answer to our question, how should you connect it to get greater charge? Not possible. So if we only have 2 combinations of connections, neither of one of those works. Okay, questions? Okay, let's do one more combination circuit. So in our last example, for a system of capacitors, we've got a potential difference V maintained across AB. We know the charge on the 5 microfarad capacitor. So up here the charge is 3.25 times 10 to the minus 6 coulombs or microcoulombs. 2 questions. Find the equivalent capacitance of the whole system, so doing our series and parallel things. And then let's use what we know, which is these 2 things, to figure out the total potential difference between points A and B. So it's similar to what we did last time, but we're sort of doing the bits in a different order. So let's get our equivalent first. So to start part A, rather than scribble on this diagram, I'm going to draw it again. So point A goes to one capacitor, goes up to another capacitor. So this one is our 5 microfarads. This one is our 8 microfarads. We want to grab our most obvious connection first. These 2, the 5 and the 8, they both connect to the same place. So our 5 and 8 are connected in parallel. We know that C equivalent in a parallel combination is when you just add them up. So I got 5 microfarads plus 8 microfarads to give me 13 microfarads. Okay, so there's my first one. Now I draw a new diagram. So I've got my point A and my point B. Now I'm taking out that parallel combination and I'm putting in my 13 microfarads, the equivalent. So I got my 9 microfarads here and my 10 microfarads here. If I look at these capacitors, these are all connected in a row. They're going to have the same charge. So they're a series connection. So I have to do a series addition. 1 over C equivalent is 1 over 10 microfarads plus 1 over 13 microfarads plus 1 over 9 microfarads. That gives us a C equivalent of 3.47 times 10 to the minus 6 farads. So 3.47 microfarads is our equivalent capacitance. Right there. Okay, we draw the picture one more time. And we've got 3.47 times 10 to the minus 6 farads. So this is my answer for part A. My point A and my point B. I'm asked to find the potential across these 2 points. When I look at this capacitor, I know the capacitance, I don't know the charge, so I can't look at this last step and find the potential. I don't have enough information. So let's come back to this picture. I know that all 3 of these, because they're in series, they will all have the same charge, so I definitely know that that's true, but that doesn't really help me that much either. It'll give me the potential on one of them, but it won't give me the whole deal. So now I'm going to come all the way back up to this one and ask, what do I know right here? This one I know a little bit more. This 5 microfarad capacitor carries a charge of 3.25 times 10 to the minus 6 coulombs. So this capacitor right here, I know the capacitance and the charge. I can find the potential across this one. So my potential, delta V, is equal to Q divided by C. So 3.25 times 10 to the minus 6 coulombs divided by 5 times 10 to the minus 6 farads to get a potential of 0.65 volts. Okay, when I know the charge and the capacitance, I can find the potential. These 2 are connected in parallel. And the parallel combination gave us 13 microfarad capacitance. So this has to have 0.65 volts. Okay, because that one is the parallel combination of these 2. If I know the capacitance and the potential right here, I can find the charge on this one. Q equals C times delta V, 13 microfarads times 0.65 volts. To get me a charge of 8.45 times 10 to the minus 6 coulombs. So now I know the charge on this capacitor. All these 3 are in series. They have to have the same charge. And this series equivalent also has the same charge. So this one has to have a charge of 8.45 times 10 to the minus 6 coulombs. Okay, so I've worked through my series in parallel, remembering same potential, same charge. Now I have the capacitance and the charge, so I can find my potential. Delta V equals Q over C. Gives me a potential of 2.44 volts. So pretty much with these problems, I guess your strategy, if you can't see the entire picture when you start, your strategy is to find charge and potential every place you can. That'll get you to your answer. So every place that you know 2 of the things, you can find the 3rd thing. So that's kind of the idea when you're doing these. Okay, we still got 5 minutes and I don't want to quit just yet. So let's just kind of introduce the idea of energy. And we should be able to write down that equation before we have to quit. I like these PhET simulations, so I'm going to switch over to the one about energy. This one is really silly. So this is John Travoltage. So he scuffs his feet on the carpet, and he gets all ridiculous, right? And let's have him put his finger towards the doorknob. Okay, that's it. That's all that does. Probably everybody is familiar with that happening in their life. You know, you scuff on the carpet and you touch a doorknob, or you touch your friend, whatever. You feel it, and there's a lot of energy in that spark, right? So there's lots and lots of energy. That's why it hurts. That energy makes it painful. So that electric potential energy, the way it's stored in the capacitor, that's the bit we're going to look at next. So let's remember how we said we charged up a capacitor, and what even is that electric energy? So the chemical reaction in the battery makes the charge move through the battery. That's what that chemical reaction does. The charge moves around until it hits the plate. Eventually the plates get all charged up and the charges stop moving. So we talked about that. We know that all of the work that went into moving these charges gets stored as energy, and it gets stored as electric potential energy. The place where the energy is stored is actually in the electric field itself, and that's where gravitational potential energy is stored. It's stored in the field. So a field is not nothing. It's a real actual thing, even though you can't see it or feel it, but the field is real and it is able to store energy. So that's where the electric field energy, the electric energy is. It's in the field. So what happens is our battery does work to move the charges around. The battery does work to move charge. The work put in equals the potential energy stored. If you're interested in that derivation, you can read through your book for it. That derivation is not really one of the outcomes of this class, so I'm going to go ahead and give you the equation. The total amount of energy stored is the net charge on the plate squared divided by twice the capacitance. So U is the energy stored, Q equals the charge on the plates, C equals the capacitance, and delta V equals potential across the plates. And we should remember the relationship here that Q is equal to C times delta V, and then often we're going to be thrown in that C is A times epsilon naught over D. So those are some important equations to keep together for this section. If we put in C times delta V in this expression, we can come up with 1/2 times C times delta V squared, or 1/2 times Q times delta V. So there's how we can find the total amount of energy stored in a capacitor. I do have a pretty fast plug and chug example, but I don't know if it's 2 minutes fast. So let's quit there. We're back here on Wednesday. This week is one of those funny weeks. Thursday follows Friday's schedule, so we're in class on Thursday this week because it after Friday. Yes.